let's start. So guys, again, I hope you do not shy away from showing me your faces, as that helps me quite a great deal to see whether my explanation was understandable, and of course to get familiar with you. So last class, so again guys, before we begin, do turn your cameras on if it's not a terrible inconvenience. Please note, we will see of course what happens when we approach the final. All right, let's begin, guys. So last class, we spoke very briefly about the intuition behind probability, which for most purposes will be completely sufficient for this class. So we think of probability as the limit of an indeterminate sequence. And we believe, simply philosophically believe, that that limit converges. Right? That's the philosophy. That's similar like the philosophy of calculus when we calculate instantaneous velocity, is that when time interval is short, very little change can happen in a short interval of time. So here we believe that most things that we study have probability limit. In other words, when we run an experiment that is not predictable, what will happen is that the frequency of some particular outcomes with this experiment will be the same with enough repetition, right? So for example, when we toss a coin, we see that the probability is 1/2. We mean that if we look at all outcomes of tossing a coin, as the number of tosses approaches infinity, we will inevitably notice the number 1/2 appearing. Good? That's the idea. And I hope you understand that it's not at all inconceivable to imagine that many things do not have probabilities. And definitely that things that do have probabilities, if the probability is equal to 1, that does not mean that the event always happens. And if the probability equals to 0, it does not necessarily mean that the situation can never take place. Why you used to the other mode of thinking is because when you imagine looking at, let's say, tosses of coin, no matter where in the sequence you look, you have the sense that there is this kind of like when you turn on the TV and there is no signal, you see this snow, what they will call it. You have this white noise, right? It looks like snow is falling. No matter at what time, no matter in what day, it looks the same. Right? So usually when probability is 0, no matter where you look into the sequence, you don't actually notice the outcome occur. And that means that when probability is 0, you tend to expect that something does not happen, even though it's not necessarily true. Good? And we will see later on when we talk about continuous distributions that the situation where probability is 0 and something does happen is very frequent. Now, axiomatically, I just mentioned, what do? We are going to take the space of all possible outcomes, and we call it the sample space. And every subset of that space we call an event. And we define, here I just gave a brief description of possible sample spaces together with possible events, right? And events are just subsets. And that means that any intersection of events is an event, any union of events is an event, the empty set is an event, and so on. And then we said, without much understanding, is that, again, those are the Morgan laws, some unit laws. We said that probability from the axiomatic point of view is a kind of function defined on the power set of the sample space, and producing always numbers between 0 and 1 by axiom 1. So for every subset of S, that means the probability is supposed to be between 0 and 1. And you can see why we would make such a hypothesis, because we measured intuitively as a running frequency, right? So we imagine that we count all the possible outcomes on the denominator, and the numerator we count the frequency of occurrence. So we just have number of trials is what we have on the denominator. Number of successful trials is what you have in the numerator. And that ratio, number of successes does not exceed the number of trials and cannot be negative, right? So that's why axiom 1 is rather intuitive. Axiom 2 also fairly intuitive, right? If we consider success any outcome of the experiment, and of course, every time we perform the experiment, there is a sort of outcome, and we get the running frequency equal to 1. So we define that the probability of the sample space is 1. And axiom 3, the least intuitive of all of them, we say that if we have a disjoint sequence of events, they are mutually disjoint, then the probability of their union is the sum of their probabilities. So by axiom 3, strictly speaking, we must have an infinite sequence of disjoint sets to be able to apply it. You understand? So again, guys, I mentioned that if the sample space S is too large, such a function cannot exist. That's measure theory, okay? This function satisfies measure theoretic properties, and if S is large enough, then that function cannot be defined. In other words, by the axiomatic approach, there are inevitably events that do not have probability. You understand? But we ignore that difficulty because we will not consider such things. Okay, I try to give you an intuitive idea of why some things might not have a probability. They're mathematically rigorous sets that you can prove they have no probability. And then we measured the probability of the empty set. What's the probability that nothing happens? Intuitively, we know the answer. Intuitively, if when you perform the experiment, something must happen, the probability of nothing happening is 0. Yes, but we are, when you do axiomatic approach, we are completely blind to the meaning, which means that that I need to prove it. And so remember what I decided to do. I didn't do it like I wrote in my notes. I just noticed that the empty set is a disjoint union of itself, right? And then I can apply axiom 3, and probability of a disjoint union is the sum of those probabilities. Now, this series must be convergent based on axiom 3. And if it's a constant convergent series, that means that the terms of the series, the sequence terms, must themselves be 0. Right? If you don't remember, guys, I can, after class, I can give you a brief reintroduction. You can, of course, rewatch some of the previous recordings. Good? So I know that the probability of the empty set is the sum of those probabilities. That's my explanation here. And that means that that probability of the empty set is the empty set. Have you tried, guys, to prove that the probability of a finite mutually disjoint sequence is the sum of the probabilities of the events that make up that sequence? So how we do that? Naturally, we can extend it and make it an infinite sequence. We now know that I can say En plus 1, En plus 2, and forever on. I can call those terms the empty set. Yes? Now we know that probability of the empty set is 0. So now look at it. So I now have that, that the union of the finitely many Ek is now augmented to be the infinite union, which becomes a series. Now that series has the head containing the finitely many terms, and after that head, everything else is just addition of the 0, right? Because it's addition of probability of the empty set, which makes it the summation k1 to n probability of Ek, right? So what I just proved axiomatically is that the probability of a finite disjoint union is the sum of the finitely many events, probabilities of the finitely many events. Would you like to try, guys? I will give you 4 minutes maybe, right? No more. I don't have time for that, but if you would like, try to prove the next proposition. You see, there is that proposition, you see? Prove to me that using the axioms of probability that the probability of E complement is 1 minus probability E. Can you do that? Right? In other words, the probability that E doesn't happen is the probability, it's 1 minus the probability that E does happen, intuitively speaking. 2 more minutes, guys, and then I will explain. All right. I suppose not all of you are working with that, so I guess you are ready. So here we go, guys. So here is how we might try to do that. So observe that the sample space S is always the union of E and E complement, right? So for any event E, either it happens or it does not happen. And of course, the possibility that something does or does not happen, well, we don't believe in it, right? We don't, in the naive idea of the word, we don't imagine that something does and doesn't happen. It's only maybe in quantum physics, maybe, right? So here it is. The intersection is the empty set. And so by the previous result, I know that 1, that's the probability that S occurs, it's the probability of E union E complement. Now, by previous proposition, if I have a sequence of finitely many events that are disjoint, I can just split it up like this. Yes, PE plus PE complement. And so now I see that probability of E complement is 1 minus PE. The next proposition, well, I want to show that probability is increasing. That means that if E is a subset of F, the probability of F is at least as large as the probability of E. Also natural, right? If I consider more things as successful, then the frequency of successes will be higher. So how do we do that? Well, we can go again to the same idea. So S is equal to E union E complement. And so what is F? F is the intersection of S with F. Do you agree? Because F is smaller. So we can write it as the intersection of E union E complement with F, which means E intersect F union E complement intersect F. And of course, EF and E complement are pairwise disjoint. The probability of F is the sum of those probabilities. Yes? So what do we have? We have that probability of F is, what is this? Look at it. Intersection of E and F is just E because E is a subset of F. So this is just E. So we have probability of something plus probability of some other event. And by axiom 1, it's a probability of anything is bigger than or equal to 0. So I'm only making it larger maybe. So we have probability of E plus probability E complement F that must be bigger than or equal to probability of E. Good. Now the last one. This one is very important. We will use it frequently. So what do we do when we do not assume that E and F are disjoint? Right? E and F are not disjoint. So I'll show you how to remember that formula very easily, right? So probability of E union F is equal to probability of E plus probability F minus probability E intersect F. Now you can, if you want, draw yourself a sort of Venn diagram. And this is E. And this is F, right? So doing probability is essentially like doing counting. So what do you have? Probability of E union F. It's the probability of E plus the probability of F. But when I count the probability of E, I count the intersection once. And when I count the probability of F, I count that intersection one more time. So I counted the intersection 2 times. And therefore, I want to subtract the probability of the intersection. Yes? So it's very natural out of a Venn diagram to see this result. Now let's do that result formally without a Venn diagram. So here is the situation, guys. So I can only add up easily events that are disjoint. So I can write E union F as what's in E together with what I did not add with the residual, which is what's not in E but is in F. Do you agree? So I clearly see that E union F is the same as E union E complement F. By the way, guys, I clearly see that. I'm not missing any of you, or I'm not missing too many of you, correct? You are with me. You understand what I'm saying. It's not just to myself that I'm so clear. So what we have here is wonderful. So far, good. This is also not the most important thing in this class, right? I mean, we are going to move to something nicer, hopefully today. It's not my favorite thing to explain. So probability of E union F is that probability of E plus probability E complement F, right? Because I know that we proved that finite disjoint sequences are also additive. And so what do I have, guys? Look at it. So it's probability of E plus probability E complement F. Now you need to recall, what is F? Probability of F is probability of E intersect F plus E complement intersect F. You agree? What's in F? It's what's in E and in F and what's not in E and in F. And so that's the one I want. So look at it. I can replace probability E complement F by probability F minus probability E intersect F, whereby I have this desired formula. Now, once I establish this intersection for 2 sets, it's very easy to extend it to 3 sets or more. Let's do that extension for 3 sets, for instance, right? So if I have a triple union, I can group it as a pair union with I can two of them together with the third, okay, like this. So I can apply the previous proposition for the event in red parentheses and G, and that gives us probability E union F plus probability of G minus the probability E union F G. Yes? Now, what is this result? Look at it. So now here I have probability E union F. I can apply that theorem again, and you can see where it's underlined in blue. Here is that idea applied once more to P union F. So I have PE plus PF minus PEF. And here we have plus PG. And here I just distribute the G through the parentheses. So it's PEG union FG. And then here I apply the theorem one more time. You see, so I apply it here. It's a union of 2 events. Applying it one more time gives me this result. It's the sum of all singletons minus every pair plus every triple. You understand?
Professor.
Yes.
In the first result, why aren't we subtracting P E union F intersection G?
Where here, what we're subtracting here, you're saying?
No, on the last line, just before that.
On the last line?
No, the fourth line from below.
So it's just essentially, I mean, you can just see if you can do it afterwards on your own. It's essentially just a calculation. If you understood how to do it with two events at a time, you understand how to do it with 3, because you can just group those as 2 and apply, and now it looks, let's see, with the red parentheses, it's now application of probability of a union of 2 events, which might not be disjoint. And so you obtain the situation. It's probability of the red parentheses plus probability of G minus the probability of red parentheses intersect G. Now, here we have, again, probability of a union of 2 events. So I apply that formula, right? So here everyone is clear. Here you see, well, if it's in E or in F and in G, it must be either in EG or in FG. This thing is here. You see, this line is this this thing is this thing. Hopefully that's clear. And then here I now again have union of 2 events, and I can just apply that result one more time. And when you apply it and arrange everything neatly, you get sum of singletons minus every possible pair plus every possible triple. Do you understand? So this formula will be important. So for instance, suppose that that if I had four of them, I'm not sure if I want to write all of them, but imagine that I say probability of E1 union E2 union E3 union E4. Okay, if I had four of them, what will you observe, guys? You will observe first it would be the summation of every singleton, right? So that would be, let me write it like this, probability where k starts from 1, goes all the way to 4 of p e k, right? It will be summation of every singleton minus, I will write this symbol. Now I need to consider the summation where I have every pair combination. So that I can write as a summation of where I1 is less than I2, probability of EI1, EI2. That means every pair. How many terms do you think will be in that sum? Anybody? How many terms will I add up in that sum? The summation ranges over how many terms? 3. Okay, maybe, but in general. So in general, it is it 3? Be careful, right? Think about it for a second. You see here it's every combination. How many combinations are there of 2 events at a time? Yes, good. The answer is it 4? Is it 4? Look at it, guys. So you have a combination of 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, 3 with 4. Not 7. Oh, you see, look at it, guys. You're missing. You're. It's like, I think you're playing Battlefield, right? Have you been watching Dunkirk recently or something, right? So you are trying to sink my ship by just randomly shooting at it. 8. Oh my God. I mean, what are you trying to do here? Carpet bomb me? Look at it. How many combinations are there? I can have 1 and 2, 1 and 3, 1 and 4, right? Then I have 2 with 3, 2 with 4, right? Now I have 1, 2, 3, 4, 5, and I have 3 with 4. They are exactly, well, and 3 with 4, it's one thing. I mean, right? 3 and 4. So I have exactly 6 combinations. Do you see? Now, did I need to actually list them out to know I have exactly 6 combinations? Think about it. No, obviously I didn't have to do that. Why? Because we have now 4 events, right? When I take the intersection, I make a selection, which is first, which is second, right? I place them always in order. So it is 4 choose 2, which is 6. 4 choose 2, good? So it would be minus the pairwise probabilities, the sum of all pairwise probabilities, plus the sum of all triple combinations. How many terms do I have here, guys? Yes, which is, in this case, it's 4. If I have triple combination, I can think about the guy that's missing. Either 1 is missing, or 2 is missing, or 3 is missing, or 4 is missing. So that would be 4 choose 3. You all see that? And minus the probability of E1, E2, E3, E4. All combinations of 4 at a time. You understand? It goes plus minus all the time, where you begin plus every singleton minus every pair, plus every triple minus every combination of 4, whatever it is, right? So so it's like this, you see? On even, when you have evenly many, you subtract. When you have odd many, you add. That is the pattern, and you should convince yourself. It will be, we will see later on examples where inclusion-exclusion formula is the best formula to use. At least, I mean, it's very difficult to come up with a better solution if you don't use it, okay? Let's go back to the lecture. So that's what this is. The situation is in general. Do you understand? I record that situation in general. Here it is, guys. If I have n unions, so that's the formula. And what that formula is saying, guys, all it says is something very simple. It says, begin by adding every probability of a single event, right? Subtract every pair, then add every triple, then subtract every 4, then add every 5. And you do that plus minus until you reach the number n, okay? And if I intersect events, I can obviously list the events from smallest event I'm intersecting to the largest, okay? So whenever you think about listing combinations, think about a document and think about how you present that information. If I selected, let's say, if I select 5 people out of 30, I can list the people I selected by the lowest number first, then the next lowest number second, all the way to the largest number I selected. You understand? So that's why you know this. If you intersect any R events, I can list it as I1, I2, all the way to IR. I list them by rank, and the sum is taking place over n choose R terms. That's going to be important. You have to know how many terms you're adding. Not just the summation, but remember over how many terms you're adding and how do you arrive at that formula. Convince yourself, you understand? Play around with it. You can prove it by induction or come up with another argument. On page 7. Which part of that result bothers you? Let me see. So again, right? If you understand, if we had pairs, right? You understand the idea is that you can reduce the process if you have a pair. If you understand what happens with a pair, a triple can be reduced to a pair. We did the same idea with the basic principle of counting, correct? So if I understand how to deal with 2 experiments, and I know how many outcomes in this experiment and how many in the other experiment, I know I need to multiply the number of outcomes of first experiment times the outcomes of the second experiment, right? That's how I count the combination of experiment 1 and experiment 2. And that allowed me to generalize it to any number. How do I generalize? I group 2 experiments at a time. So similarly here, I have a triple union. So I do that 2 at a time. You see, so I decided to say if it's what's in E and in F, it's what's in EF, E or F, and or G. You understand? Sorry, I said and or, but you know, right? So if it's either in E or in F or in G, it's the same as saying it's either in E or F or in G. Good. And then from there, I just apply this formula that I obtained when I deal with 2 events at a time. I apply it whenever I see unions of 2 events.
Professor, the last 2 lines are one equation, right?
All of it is one equation. I mean, it's just derive it. I mean, don't really even bother looking at my equation, derive it, because you would forget it. It will not be in front of your hands.
I see.
Right?
Thank you, Professor.
Right. So derive it, guys. And if you have questions, then ask. But try to derive it yourself. Try to be sure that it's very intuitive to you, and make sure that you understand all aspects of the inclusion-exclusion formula. Okay. Here is a small question, right? I have 2 cats. Cat A irritates me with probability 0.95. Cat B irritates me with probability 0.01. What is the probability that I will be irritated by neither cat? And assume that the probability that both cats bother me is 0.005, okay? So if you understood it, do a quick calculation. What's the probability that I will not be irritated by either of my cats? By neither, guys. Make sure that you understand by neither, right? So come up with a symbol and then reason it out. All right, you're ready, guys? Yes. So I mean, don't worry about calculating it. Only worry about the symbols. You have to be good with symbols. Everything else, I mean, you can do it, right? So okay, let's set up notation. Good. Let's set up. Thank you. No, set up notation. So A is the probability I'm irritated by cat A. B is the probability I'm irritated by cat B. Yes. So guys, so what is probability A union B? Make sure that you understand my question. Probability of A union B is the probability that I'm irritated by either cat A or cat B. I ask you for the probability neither cat A nor cat B irritates me, yes? So let me first calculate probability I'm irritated by one of the cats. So that's probability A plus probability B minus probability A intersect B. So that I just add up the probabilities of being irritated by each of them individually, subtract the probability of being irritated by both simultaneously. And I arrive at the number 0.955. Good. So the probability I'm irritated by neither cat is the complement of the event A union B. And you remember that to calculate the complement, it's 1 minus the probability of A union B. Yes, the neither thing. Just so it's fine. I mean, you will see later when that becomes more important. That's a still trivial question. Yes. So what we have is 1 minus 0.955 is equal to 0.045. Good. So that's the probability that I'm not irritated by either cat A or cat B. It of course doesn't mean that I'm not irritated. Let's go to the next lecture, guys. Sample spaces having equally likely outcomes. So when you think of probability, the most natural place to start is when you have outcomes of an experiment, neither of those outcomes are preferred. Good. So that happens, for instance, when you roll a balanced die. The die might land on any side without any preference, right? Whereas when I toss in bed, I'm lefty. So I probably either toss more on my left side or on my right side, who knows, right? But probably there is a preference, right? Definitely there is a preference on which arm I wear my clock, my watch. Good. So here is the sample space S. It has outcomes numbered 1, 2, all the way to n. We say that each of those outcomes is equally likely to occur if the probability of each individual outcome is the same for all of them and it's equal to the number p. Yes? So without any problem, I can calculate what that number p must be. Because by hypothesis, when I perform the experiment, one of those outcomes has to happen, yes? Either outcome 1 or 2, or all the way to outcome n. And so probability of S means just the probability that one of them is happening. So that's 1. And that's the probability of the finite union, which I know I can translate to finite sum, which ends up being adding the probability p to itself n times. So I see that 1 equals to p times n. And therefore p equals to 1 over n. By the way, here we can also have this interpretation that if we consider S as the set of possible universes, then the outcome of a particular event, the outcome of, let's say that the likelihood of one happening, it's one universe out of n possible universes, right? So it looks like what we have to do is count the number of desirable universes and divide by the total number of universes in my sample space. And that's true for, only true for sample spaces with equally many outcomes. So coin when you roll it, the probability of rolling heads is 1/2. It's 1 out of 2 possible universes. But it doesn't work for my probability of winning the lottery today. I still either win the lottery today or not, but those outcomes are not as likely. You understand? Good. So you understand what this is saying, guys. So all you are doing, right? So you're doing a combinatorial problem. So yes, Sarah, right? So in probability, there's always this vagueness about the assumptions. Even when you write a question and you try to write it well, and I'm not always successful at it, who knows what is the assumption. So make sure to be clear about the assumptions. And of course, if you have questions, let's say for my exam, what am I meaning, you of course are welcome to ask, right? So it's just going to be a conversation. Don't think of it as a high school. So it's not like a question and here's the word and we cannot talk about it, right? We obviously can talk about it. We just cannot post it online or share it among friends under very strict penalty, right? Right? But aside from that, you can do a lot of things. All right, guys. I told you last semester, I thought, well, my probability students are, well, they're doing very well and they're interested in mathematics. And then I look at their exams and I see, well, half of them copied something, right? And so I'm going to be more careful this time. Good, I caught them. So we are going to have very little tolerance. Even though we live in New York and we're very tolerant, we will have very little tolerance for posting questions online, correct? Or sharing them. Good, so again, we have probability of any event E in a sample space of equally likely outcomes is going to be number of outcomes in E divided by number of outcomes in S. Okay, and let's try to do a first question together, guys. If 2 dice are rolled, what is the probability that the sum of upturned faces is 7? Go ahead, calculate it. 2 fair dice are rolled. I want to know the probability that sum is 7. Okay, if no, wonderful. Come on, guys. Okay, great. Andre, wonderful. Wait 1 more minute and then we'll discuss that question. It's simple, hopefully. All right, so I mean, this question seems to be easy enough for you, and let's discuss it, yes? All of you have answered it correctly. So here is, guys, but besides answering it correctly, we're developing a technique, you understand, guys? You don't always have to use the technique if the question is simple, but make sure that when you are, when you really want to be absolutely sure, you document it, right? You document it. So here is the way I produce naturally, basically a probability question of this chapter. It's just involving 2 Kafka protocols, okay? So the Kafka protocols involve a document for recording successful outcome and a document recording all outcomes, okay? So why do we know that we have 36 outcomes? Well, easily we know that we have 36 outcomes because the Kafka protocol for the sample space is outcome of die number 1 and outcome of die number 2. I can imagine either rolling the die sequentially or that the dice are of different colors, so I know what's die 1 and what's die 2. It's going to be very important not to confuse that, guys. It matters what is die 1, what is die 2, right? So it must be unarbitrary that when I read, or not arbitrary when I read this code, that I know exactly what happened. Good. So that means that the number of outcomes in the denominator is 6 squared. Good. Now the number of outcomes in the numerator is like this, guys. Look at it. As soon the sum has to be 7. So the first result must be k, and the second result is immediately determined, 7 minus k, where k cannot exceed 6 and cannot be lower than 1. But it works perfectly for the situation where the sum is 7 every possible case possible. 1, 2, 3, 4, etc. Right? So look what I did here. K, 7 minus K. I need to only specify the outcome on the first die. There are 6 possible outcomes. You're all clear? And not just by your explanation, you're clear how I am being methodical, guys, right? I'm being very methodical, correct? You understand how you behave methodically, guys? All right, so you know, I am as methodical as, you know, as Fuß, Bo, then Schleif. Maschinen Verleih. Okay, as methodic as that, and that's how you are supposed to be as well. Understood? Well, you should all read Mark Twain, The Terrible German Language. That's one word. Exactly, right? And there is, and if you don't understand, that's your problem. That's why probability seems difficult, because you are not understanding this. Exactly, right? That's exactly what I mean, right? When you understand this, then you understand probability. Always make a document. Always be bureaucratic, because it will come to bite you. So let's try to understand, guys, what does the word random mean? So we say the word random, and you should think, replace it by the word indifferent. Random means that nature or whatever performs the experiment has no preference to the success or failure of each individual outcome, and all of them have equal opportunity of showing up. Good? So we will investigate. So that's basically when you say outcome, it means you need to imagine a sample space, and every possibility of that sample space has the same probability. Okay, that's what we will say is random. So let's try this experiment, guys. 3 balls to be randomly drawn from a ball containing 6 white and 5 black balls. What is the probability that one ball is white and the other 2 black? Do you understand what I'm asking? 3 balls we're selecting. We have 6 white and 5 black. We want 1 white and 2 black. Calculate. Okay, great. We will do it in several ways, okay, guys? Because you can interpret what's happening. You can interpret the sample space in several ways and see if we get the same result. All right, guys. So you all seem to be in consensus about how you try, at least the people that said anything here seem to be in consensus. Good. So let's try to see how to solve this problem. Okay, guys. So we make several, we just examine, we're going to be a bit too pedantic about it. We're going to do it under several assumptions. So what are the assumptions? So first assumption is all balls are distinguishable. And second assumption is balls are removed in order, one after the other. Okay, I know what was the first ball removed and what was the second ball removed and third and fourth and whatnot, okay? So for that purpose, of course, I imagine those balls as having a white ID and a black ID and a population ID. Okay, so they have a lot of ID. You know, you cannot go on the streets of Germany without having an Ausweis, and ask anybody who lives there. It's true. Okay. So what you have here is, you see, those are the population. The population ID is 1 through 11, and then the red numbers. So here it is without replacement. There are so many words to use. I mean, they end up not mattering because they produce the same probability, but let's see why. Okay, guys? So we do it under this assumption, and we construct a Kafka document, as we always do. So my Kafka document is, first of all, for the success, right? There is going to be one Kafka document for the numerator, and the Kafka document for the denominator must match the procedure, okay? So in this procedure, I remove the balls without replacement, one by one, right? So I will assume that, let's say, so what my document is going to say, here is the place of I select only one white ball. What's the place of that white ball? And here is the white number I will put, and here I will put the black numbers that appeared, the black population numbers in order. So if I selected 2 black balls and 1 white ball, I need to know in what sequence were they picked. Good, and that will tell me that sequence. You agree? So my code will be 2, 3, 3, 1. What does it mean? 2 means that that the white ball is in the middle. You can see here is the actual situation that happened, right? And here I'm saying that the white ball selected is white ball number 3, and that means it's if its population is 3, that means well, what is it? So then we have so what this is saying is how many possible ways to put this information. There are 3 possibilities. Here we have 6 possibilities for the actual white ball selected, and I just chose white ball number 3. And here the black ball was 3 and 1. So first black ball chosen was 3, the next black ball chosen was 1, right? So there are 5 possibilities and 4 possibilities afterwards. You all clear? So altogether, the number of outcomes in E is 3 times 6 times 5 times 4, which is the same as 3 factorial, 6 choose 1, 5 choose 2, right? 3 factorial, because if I select them, I can then arrange them in any order. That's why I know without any calculation that this number is going to be the same as that number, okay? I'm showing a sort of equality of results, even though we don't have the same assumptions. So far, good? You understand what I'm doing, guys? Yes, I'm just being very, very methodical, and for everything, I just want to understand how I document a successful outcome. So that's document for successes. Now the document for the denominator will look like this. What was the number of the first, second, third? And that would be, I just use population ID. So that's 11 possibilities, 10 possibilities, 9 possibilities. So I calculate the probability to be 3 times 6 times 5 times 4 divided by 11 times 10 times 9. That's different from your calculations that you presented me, right? Now, is it going to be similar? Well, the number is going to be 4 over 11, but I can also write it as 11 choose 3 times 3 factorial. And here I can write 6 choose 1 times 5 choose 2. And I can cross away a 3 factorial, and I get 6 choose 1, 5 choose 2, 11 choose 3. Which, if you notice, everyone who answered, they gave me that number, right? You gave me the combination number. That's what I think Andre did, and Aaron did, and a few other people. Good? But you understand that I did a totally different procedure. I just arrived at the same result. I had different assumptions here, right? My sample space and your sample space was not the same. Do you all understand that, right? The sample space is, see, they did not have the same number. My sample space was 6 by 6-fold larger than your sample space that you selected. Andre or Aaron or anybody else who answered this question, right? And yet I get the same probability. Why is this? Okay. Now, here is the second assumption. Notice I have a very different document here. Here, I presume that the balls are distinguishable and they were drawn simultaneously. In other words, what happens is that the selection is happening all at once. Every one of the three balls is selected right away, not one after another. Okay, if that were the situation, my success document would look like this. You see my success document? I just tell which white number I received and two black numbers in order. Notice this is not a solid bar, so it's in order. So for example, if my outcome was 331 or 937, depending which code you prefer, population code or you know, using their individual color codes. Okay, so here what do I place? I place you see I place the white number, so the white number of this is 3, and here I place the black numbers that were selected. So the black number selected is 1 and 3. I need to place them in order. I cannot write 3 1. I have to write 1 3. Do you understand? And so now I can count how many possibilities are for this document to be filled in. So it's 6 choose 1 for this box multiplied by 5 choose 2 for that box. For the denominator, I use the population ID. Denominator is counting the success using population ID. So what do I do if this is this? If this came to be the situation, I write 5, 6, 10, and I write them in order. 5, 6, and 10. It's 11 choose 3 possibilities. Do you follow, guys? And I again get the same probability, 4 over 11. 6 choose 1 times 5 choose 2, 11 choose 3. I get the same probability. That's very important. So again, guys, right? We did work with different sample spaces, and we calculated. In each case, we calculated 2 combinatorial problems, one for the numerator, one for the denominator. But in those 2 assumptions, right, we had two different sets of combinatorial problems. You understand? The result was the same, but we computed 2 different sets of combinatorial problems. Now, the reason that you might expect that to work is because we consider the quotient. You understand? I mean, if the difference between my sample space is, let's say, it's 6-fold as large as your sample space, and I do correctly the numerator, it's also going to be 6-fold as large as your numerator. And so when I take the ratio, that difference is disappearing. You understand? So what you take to be your universe, you have some freeway about it if your goal is to calculate probability. That's one reason. That's the first reason you can notice that we can ignore so many factors about the environment, right? So let's say we are talking here about 3 balls being selected, but we talk nothing about the universe at large, right? Where are those balls selected? What does the ball look like? You know, on what day, right? All of those things you might imagine are not important, but it's wrong. They are not important for the calculation of probability, but they do affect potential universes, right? In other words, the more I know about the selection of those balls, the more, the less potential I have in my universes, the fewer possible universes I have. Okay, but again, ultimately, you're in the business of trying to count the the proportion of favorable universes divided by total possible universes that will be produced. Okay. And we make a lot of restrictions here. That's why this idea is so difficult, right? Look at it. We ignored everything except for those balls. So here is the observation that I would like to make, guys. So sequential random sampling generates the same probabilities as simultaneous random sampling. In other words, when I interpret random sampling, I can say that the sampling happened all at once, or it happened sequentially without replacement. You're clear? I'm going to try to explain why I can be so loose about it. So suppose, guys, that what we have here is we are going to play this game where we have n balls, n individual balls, right? So let R be the number that will be sampled. You understand? We're going to select R balls, and we will examine what is the probability of a particular selection. You understand? In other words, let's say what's the probability of picking ball 1, 2, 3, 4, 5 all the way to R, or maybe 2 all the way to R plus 1. Just focus your attention on one particular sequence, and what's the probability of getting those balls in that sequence. Okay, I don't mean ordered sequence, I just mean individuals. What's the probability of getting individual balls 1 through R, or 2 through R plus 1, or any other particular grouping of individuals? Okay, so if I do it simultaneously, guys, if I do it simultaneously, then what's my sample space? My sample space consists of all possible groups that I can obtain. There are n choose R groups. And if each of them is equally, each of the groups is equally likely to be selected, the probability I select 1 through R, it's 1 divided by n choose R. Do you see that? On the other hand, if I do the sequential probability, it means that if I want to generate the individuals 1 through R, I generate them in order, right? So there are factorial ways to select them in order. Let's say I might select 1 first, 2 second, 3 next, or any other of the R factorial ways in which I can select them. So, and then if I select any collection of R, it's just R factorial times n choose R, and all that happens is that you can cross away R factorial. You see, and that means we don't really, we can ignore sequential or simultaneous. You can decide which you prefer for the particular question. But make sure that if you selected simultaneous, simultaneous sampling for the denominator, you do the same thing for the numerator. You understand? They have to count the same universes in the same sample space. Okay. You cannot decide to count sequentially in the numerator and simultaneously in the denominator. That will create mistakes. Here is a question. A committee of 5 is selected from a group of 6 men and 9 women. If selection is made randomly, what is the probability of 3 men and 2 women being in the committee? Calculate. Karen, it's fast. Okay, some people see it fast, I hope. Okay, good. All right, so here is the situation, guys. So again, I will do it methodically, okay? And you might think this problem you can solve without thinking too much about it. Perhaps later there will be harder problems. Make sure that when necessary, you can provide a protocol, explain what exactly you're counting and why that makes non-arbitrary sense. So here is what I do. So if I'm selecting a committee of 5 individuals, I will represent my sample space document like this, right? So that means that the individuals selected, if I select individuals 3, 7, 1, 13, and 10, I have to put them in order, right? Altogether, I have 13 individuals or something like that, or 6 plus 9, right? So 15 individuals altogether I have, right? So when I select them, I list them in order. So how many ways are there to list 5 individuals selected in order? It's 6 plus 9 choose 5. That's my denominator, yes? Now, what's my numerator? Numerator is if I were successful in randomly sampling 3 men and 2 women. I think it was 3 men or 2, yes, the 3 men and 2 women. then I can place them in this document where the men are listed by their men ID in order and the females are listed by their female ID in order. Okay, so it's now very well organized. You see, let's say the people I select is 8, 4, 12, 2, and 5, and we have the men and female IDs. Right? Clear? You understand what I mean, guys, right? So you imagine that each of the 15 individuals is carrying 2 tags. They are carrying on their chest a tag representing their ranking among all the 15 individuals, and they have another tag representing their rank among their category. So, for example, men are wearing tags 1 through, how many men did I say there are? There are 6 men, right? Men are carrying men tags 1 through 6 and population tags 1 through 6. So they carry a number 1, 1, 2, 2, 3, 3, right? Women carry tags 7 all the way to 15, and 7 corresponds to woman 1. 8 corresponds to woman 2, and so on. Good? Understand? So you can imagine the tags, and then when you actually record them by the population, you can here put their gender code, which is 24526. And so you can now see that the success document E, has how many possibilities? It has 6 choose 3 times 9 choose 2 possibilities. So numerator is that number. Do you understand how I obtained it, guys? Methodically. Good? So you understand how that was carried as the calculation?
Arkady,
Yes.
can you bring that down a little bit?
Down like this?
Or up?
Okay.
Yeah. Thank you.
Okay.
No. Just
yeah, it's also, you know, it's on my website in case you want to ever look at it, right? So good. So it's there on the website.
All right.
So you don't have to focus on listening to it. You don't have to worry about copying it in time because it's available.
All right.
Okay, good.
Yeah.
You imagine it, guys, right? It's a sort of wonderfully bureaucratic word, right? And you can almost enjoy it to a masochistic extent, right? It's like a perfectly working DMV. That's what you have to think about. All right, so let's go on, guys. And here is the situation. Look at it. We can solve it in many ways, but some ways are more clever than others because they involve far less computation, far fewer computations. So imagine that we have the following. We have an urn containing n balls. One ball is golden, special, right? In other words, imagine you reach with your hand into the urn and you need to pull out a ball. And if you pull out the golden ball, you win. Good? So if k balls are randomly drawn, imagine that you reach in and you can withdraw k balls. Maybe you can withdraw 7. I'm not sure what's k, right? Any k. Randomly withdrawn, what's the probability that you will be able to find the special golden ball? See, that's calculated. Good luck. Andre, be careful. I think you mean reciprocal, right? Yeah, wonderful. By the way, guys, over the weekend, I was able to solve 2 what-when-where problems correctly, and 1 I solved reverse, right? If you're interested, I'll show you. Let's see how good is your intuition. There is 1 question that's very good about Confucius. All right? I solved it immediately. I wonder if you would. All right, guys, let's work on it together, right? So we can solve it in so many ways, okay, Sarah? In so many ways, okay? So here is 1 solution, solution number 1. So again, we imagine we assign IDs 1 through n, where with n being the special golden ball. Okay, and so here I imagine taking the sampling sequentially. So my sample space, I list in order what was the first ball withdrawn, second ball withdrawn, and so on, right? So there are going to be k factorial times n choose k possibilities. You agree? For my sample space, if I do it sequentially. N choose k for the actual collection of things that I take out, and k factorial for the order in which I took them out. Now, then I can list it this way, guys. I can imagine listing the success as first I list the moment. Did I withdraw the golden ball on my first draw or second draw or third draw? So I can write it as moment of ball n selection, and the other k minus 1, the ranking among themselves, right? Ranking among themselves. You understand? So this means this means what? Look at it. This means that I skip it and I write this this all the way to k minus 1 if that's the situation, right? It's only among themselves. So in that situation, I have this calculation. Look at it. It means numerator is what? Numerator is k possibilities for the moment at which I take away this ball, and the others arranged among themselves, n minus 1 choose k minus 1 times k minus 1 factorial. Okay? And divided by k factorial n choose k, that's the denominator. So when I simplify it, I get n minus 1 choose k minus 1 divided by n choose k, which I can convert by algebra. I can just say, okay, well, let me multiply this by n and by n. And if I multiply, the reason I do that, if I multiply this by n, I have the combinatorial identity that n times n minus 1 choose k minus 1 is the same as k multiplied by n choose k. Why is that combinatorial identity working? Think about it, guys. If I am selecting a committee of size k and I make one of the people a leader, I can either make the leader first and adjoin the remaining members as committee, or I can first choose the committee, which is what I do over here, and make one member of them their ruler. You understand? So if I have an n here, I can convert numerator to this expression. Denominator, I just simply I keep the n over here, and then I just cross out n choose k, and I have k divided by n. Right? That's an attempt to do it one way. Okay. Now here is where selection is carried simultaneously. So here I imagine listing n choose k of the balls at once. And here I again imagine that I got the special ball in, and then which remaining balls are selected. That's n minus 1 choose k minus 1, and so I get n minus 1 choose k minus 1 divided by n choose k equal to k choose n. Notice that solution 2 is slightly better than solution 1, involves slightly fewer calculations. Understand? In solution 1, I had this initial cancellation. Look at it. I was able to bring it to k times k minus 1 factorial. I was able to make it k factorial and cancel out with a k factorial. So I had a lot of terms that I did not need. Yes? You understand? The point is, my point is, obviously I'm not showing you my first solution is not as good as my second solution. And maybe I can do better. But the point is, guys, when you do it many ways, you understand that it's actually the reason the solution is different, not just algebra here, right? Is that I use entirely different methods of counting my situation here. You follow? Now, here is solution 3. So that's the more clever solution. I can imagine, look at it, guys. I can imagine that I have I actually do an entirely different sample space. I completely ignore every other ball except for the special, except for the golden ball. Now I'm going to make k samples. I can imagine it's like a PES dispenser. So the first k slots are the objects that I will get. And I get the golden ball if it is within the first k slots, okay? So the golden ball, it's equally likely, there's no preference where it's located, it's equally likely to be in first, second, or all the way to the nth position. So the denominator here, look at it, is just the place within the path dispenser of the special ball. Good? So there are n possibilities in that sample space. Now, do you understand, guys, what I'm saying? In all three examples, I use a different sample space. And E, E must be, it's the same thing, but only it has k possibilities, because if I am to select the special ball, it has to take position 1 or 2 or all the way to position k. Yes? So that's why it's k divided by n without any extra calculations, which perhaps because some of you wrote it, like Andre and a few other people, maybe you right away saw that fastest way to calculate it, immediate way. Yes? But you understand, guys, so you have this methodology. You see, so when you write your solution, I like you to also present it in this way to show me that you understand the methodology in case you do want to use it. Good, so that it's very methodical. What is it that you're communicating? How do you carry out your counting? Yes? Anyone wants to ask me something? Go ahead, Sarah.
So I did it that last way, but now I'm thinking, wouldn't it be the first one has 1 over n, and then the second one has 1 over n minus 1, and then
well, be careful, because you might have learned something else, but you're not doing the sample space thing. We haven't learned why we multiply those probabilities individually. Right now we use it, we look at it this way. Our picture is this: every outcome, every node, every point in my sample space is equally likely to occur. Yes? Now, what are the nodes of my sample space? They must involve all universes that can come about, right? And then you decide what are those universes. So in my last outcome, I was not multiplying anything. Notice, I just said, okay, the universe is reported as 1 all the way to n. So I have universe 1. Universe 1 means the special ball is in first position. Universe 2 is in, it's 2, it means in second position, right? So I have n universes. My success is k out of those n universes. Universe 1 to universe k is where I select the ball. That's how I decided to model the last situation. Right? In the previous situations, I actually included the other balls as part of my universe. Right? So you see what I'm saying. So you're jumping through certain. You have to specify what is it that you're reporting. Right, in the last idea, I'm just only reporting the position of the special ball and nothing else. And that's the quickest way to solve this question, perhaps. Okay, but in previous questions, I reported why was the calculation longer? Because in the very first example, look at it, I reported more about the universe. I said in which order were all the balls selected and where did I find that ball, right? So I actually mentioned the others. But here I just now produced a different report which completely ignores all others. You see, I use a sort of common sense here, or intuition or philosophy, is that if all the outcomes are equally likely, I can think that there is no preference to where the special ball is located. There is no preference to that. So I can just focus only on that. That's the idea, right? So the idea is you really have to be careful about choosing the right sample space. Good? All right, guys. So I think for today, it's 6:50 that we end, right? So the time is up. If you're interested, you can stay for office hours to talk about something or ask questions. And if you're interested, would you like to hear the what, when, where question? Or am I torturing you if I show it to you? Right? Or, I'm trying to see if I can train myself to solve them better. So what will it be? I see 5 people run before I could notice, right? Some people give me this Cheshire smile. They kind of do this, and that's the last thing that remains when they disappear. Yes, what, when, where? Good, Alan, right? Some people, my old guard. Exactly, Aaron, right? And you see, I will show you. I mean, I'm sorry for anyone that has seen this question, possibly, and if you have seen this question before. But I will show you one that I solved, and if you have energy, I'll show you one that. All right, so let's get on with it, okay, guys? I'll stop recording.